officially working with me and with Shen, but he has done all of his work basically alone, and he's going to present an idea he had and developed during his PhD, which is not 100% new, but he has really developed a lot of theory, and it's very interesting. Alejandro, I don't know whether you have slides or you want to hand wave your way through the idea.
I have no slides, and I'm not planning to talk much about my idea. Maybe at the end, if there is enough time. I want to give more a general introduction to gravitational wave modes and to talk a bit about gravitational waves in general.
Wonderful. I like this. So it's up to you. And people in Cuba, please stop Alejandro and ask him, as usual, he's a very nice guy, he doesn't bite, etc.
Okay, then I will take over. Yes, as I'm saying, or as I was saying, I will talk about gravitational wave modes. Of course, I will speak in the next hour what I mean by this, but in particular, I want to say, my idea is not to give you a very accurate or mathematical rigorous introduction to this topic. It has, I think, quite nice mathematics, but I think the spirit of this meeting is more like to give you an idea of physical problems of what is happening. So my plan is just to go through some points which are important for gravitational waves in general, and in particular for modes, and to interact with all of you, let's say. I will not be telling you all the time, this is what happens, this is what happens, this is what happens. I really hope to have a discussion. So I also will be asking you for your opinion or what you think. And I also hope to take from this maybe some inspiration for my own work, because as Paul says, I have been working on gravitational wave modes, and this may be the strongest topic in which I'm in. But I'm a PhD student, so I have still a lot of things to learn, and I hope, by having some discussion with you, maybe I will also get some new insight. So, okay, as I say, the topic is gravitational wave modes. Let's start by the first part, by gravitational waves. I guess you have already heard some talk about gravitational waves during this meeting, or maybe have read or worked on gravitational waves in general. But just to start refreshing your minds, let's say, I would like to start with a simple question, like, if you would have to explain to someone what gravitational waves are, maybe to someone who is not an expert of the field, how would you describe gravitational waves to this person? Is there anyone who wants to share his thoughts with us?
I am sure that Benny has an opinion about this. Or Diana, or maybe Oris. Oris, it is you. Go. Come on. This is so painful.
I'm not expecting any accurate definition, but I would like actually to hear maybe 2 or 3 opinions so that we can try to come up together.
Yes.
With some good explanation, like.
Fernando, can you force some of them to give an answer?
Hi.
Hi, Jose.
Hi, could you repeat your question? I lost my connection.
Okay, the question is basically, if you would have to tell to someone who is not an expert in physics, what are gravitational waves? What would you say? How would you explain them to them?
I don't know, perhaps like a space-time perturbation due to gravitational force.
That's a very good and important part. Any other ideas? Maybe to add something up to this good starting?
Maybe I'm not from Cuba, but maybe I could offer one.
if I was speaking to someone with no background, I might say, if the universe is like a big pond, then gravitational waves are the ripples in the pond when something moves or things smash together or something like this. And the bigger the event, the higher the amplitude of the ripples.
Yeah, that's also like an important part, like as Jose said, first, like this are perturbations, but this, like, it's not a perturbation where you are just shifting all your universe to the left or something like that. No, it's more like ripples, or it's some oscillating perturbations. So we actually already have like the first 5 or 6 words of my own definition, which is oscillating perturbations of the space-time. But there's also another important point when you talk about gravitational waves, or maybe about gravitational radiation. Does someone have an idea what is also important to tell about them?
Which carry energy, is that it?
Not exactly. No, I was more thinking like that propagates. Because actually you could have something oscillating, some perturbation, but it just stays at the place where it is produced. But what is very important for gravitational waves is that they are also traveling towards infinity. So, and that's also what makes them interesting for us. This is a certain perturbation of the space-time, but it's not staying at the place where the perturbation is formed. No, it's traveling up to infinity, for example, to us, to Earth, which make them very nice carriers of information. Of course, the transport of energy also plays a role, but what I was aiming at is it is being transported. So, okay, again, like gravitational waves are just some oscillating perturbation of the space-time that propagates towards infinity. So they are formed. First, they're very violent. Somehow, just there is some system, let's say, wiggling. But then after a while, they become nice waves and travel outwards. Okay, and you already mentioned the amplitude. The amplitude is some property of a wave. So, but which other properties do waves or gravitational waves have or can have? Any ideas?
I think Diana was trying to say something before, but I mean, since Cuba people are so shy, anyone can say anything.
Are you asking for the properties of the gravitational waves?
Yes,
Some of them?
or of waves in general, yes.
Interact weakly with matter?
Yes, this is also true for gravitational waves. No, but I was thinking on a more basic level, like what is a wave
Propagate with the speed of light?
Sorry again? Propagating with what?
With the speed of light?
Yes, that's also part. But we already heard, for example, waves can have an amplitude. So an amplitude basically represents how strong or how violent this is. But what do you usually need to describe a wave except of just its amplitude? Because the amplitude could be just some regular shift in some direction.
Its frequency, I guess.
Exactly. This is also a very important part of waves because, like, let's say you have the amplitude which tells you, okay, this is this big, but you want to know like how often this happens, and this is described by the frequency or by the phase, which is like how much frequency you accumulate in time. So, and there are two other properties that are maybe more subtle or do not come that easy to your mind. One is polarization. So, like, you have your wave, and your wave is somehow oscillating.
Live streaming is on.
With a certain strength and with a certain periodicity, which is described by frequency. But because gravitational waves are waves in space-time, they also have some direction. And this is basically described by the polarization. And for gravitational waves, there are two kinds of polarization. And one is usually you call the plus polarization, which you can imagine like if you have a circle and the gravitational passes by, then you usually assign your plus polarization to be aligned with your x and y axis. So when a gravitational wave comes in, this circle gets deformed, like from initially being a circle to get an ellipse along the x direction, and then to ellipse along the y direction. And then you have the second polarization, which is the plus polarization, the cross polarization. Yes?
When you say a circle, what do you mean? Because I'm thinking on electromagnetic waves, that is the electric field vector that makes a circle when you see it, when it comes to you. And it can be linearly polarized, circularly polarized. But when you say a circle, what is the magnitude? What is the circle? I don't know.
Okay, very good question. Like, the point is like this is more kind of a thought experiment. You can imagine like you have some point masses. You make them fly somewhere on your so that they're organized that each point mass has is on a circle, and you could imagine, for example, you are connecting them by lasers. So what I mean by that the circle gets deformed is basically when the gravitational waves comes in, certain points or certain emitters of the light get further away for a moment. Basically, when your gravitational wave is going up, like if you might imagine a sinusoidal, like it's going up, so it gets stretched in a certain direction, and then after it reaches a maximum, it gets squeezed again towards this direction, but then it gets stretched in this direction. So this is this stretching or this deformation. It's not something like the electric field or something. So it's not that this is a direct physical quantity you can measure. What you can measure is basically, depending on which way you describe, but you could more imagine like, okay, the position of these two masses is what is changing, and this is what you can see. So yeah, like the physical effect is really like the space-time between point masses gets stretched or squeezed.
So you mean like a proof mass?
Yeah, for example, like
that you see the effect
mass
of the gravitational. Yeah. Oh,
yeah.
Thank you.
Yeah, for example, for what LIGO basically does, I mean, you can imagine that if you have this circle, you could set your LIGO detector, which is L-formed, to be like along the X and the Y axis. And so basically you are only seeing 2 points of your circle plus the center of the circle. And LIGO basically is, okay, at certain times, one arm gets stretched and the other gets quenched, and then in the other direction. And this is what we can then detect as a gravitational wave.
Yeah, I have a question, please.
Yes, of course.
I would like to know about the other properties of the electromagnetic waves in the diffraction and the interference.
Okay, this goes very far away for where I was planning to go, but briefly said, most of the properties that you have for electromagnetic wave also are fulfilled by gravitational wave, because this come not from being gravitational or not being electromagnetic, it's just come from being waves. So for gravitational waves, you also can have some interference. So if you have some ray of gravitational wave coming in from this side and others from this side, and they happen to cancel out perfectly, they also can interfere and cancel out perfectly. So these kind of things you also can have. In principle, you also can have things like reflection or absorption and these kind of things. How strong they are and how they really work are a bit different, like depending on how strong your gravitational waves force couples. And these things, maybe when you're interested in these things, one point that is important is that usually the frequency of gravitational waves is much, much larger than the typical frequency of light. So, for example, for scattering or interference and these kind of things, while for light you always can treat it, or almost always you can treat it just as some ray, like in the so-called geometrical limit. For gravitational waves, this sometimes change, and you have to really take in care that these are waves, and it's not so easy to describe them simply by ray in more cases than for light. But except of that, let's say to a basic level, you can say that the properties are pretty much the same.
Thank you.
I have a question.
Yes.
Okay. Is there any specific reason to believe where the main cause that the gravitational waves propagate in space-time? I mean, when you resolve the wave equation for electromagnetic wave, neglecting the fact that the electromagnetic wave is composed by photons, I mean, just as a wave, you need to resolve the wave equation and you obtain of one of the solution, the harmonic solution, and you can infer that you are going to have a wave propagating in space. So, is there any reason to believe that the gravitational wave needs to propagate into space?
Sorry, can you restate your question? I actually don't get what you really want to know.
I mean, when you have a fluid, a way into the fluid, the different particles inside the fluid are connected between among them, and one perturbation is going to go to the next particle in that way. But you, in that case, in a medium, for instance, when you have an electromagnetic wave, you don't need a medium to propagate. But when you resolve the wave equation, one of the solution is the harmonic solution, and you are going to have a wave propagating in space. So let's see. The space-time points are connected between them. When you perturbate this space-time point, how the next space-time point feels that perturbation? What is the reason of the next space-time point need to feel the perturbation of the before?
Okay. Honestly speaking, I'm not the best person to answer this question in rigorous enough, but what I can tell you about this is the gravitational waves are, strictly speaking, not something which is propagating in the space-time. It's part of the space-time. It's really a deformation of the space-time itself. So, and in general relativity, how you describe the space-time, these are, of course, not like some particle one after the other, like in the fluid. It's really just a smooth space-time. And what you actually find is that basically when you have some perturbation, there are maybe some perturbations which can stay locally, but some other kind of perturbation just move away, let's say. What to say? Yeah, so I cannot, to be honest, I cannot tell you why they need to propagate, why they cannot just stay there. But if you make the analogy, something like with the water, okay, of course the water are particles, so it's like the fluid you were mentioning, but basically when you have some overdensity somewhere, this try to relax, and this relaxing is usually done by nature, causing some kind of wave. So gravitational waves in many systems, gravitating systems, you can say they take this this task of taking away the energy or the linear momentum that you have too much. So that's like how I would try to answer your question. I hope it helps you.
I have more question about this, and maybe you could help us. In this moment, as far as I know, you professor, you are deforming the space time, but just a little,
yes,
because your mass is very low. So when you are moving around your house, you are producing gravitational wave, with a small amplitude. If you are a more
only if you're accelerating.
Yeah, actually only if you're accelerating, yes.
Okay. So what I mean specifically is when I have read about the history of the fluid and the wave in the physics, this is the first step on all the knowledge. I mean, you know the wave, but you don't know how the waves propagates. So it could be about the propagation of the gravitons in the universe as a gravitational wave, or there is not any relation with this.
Okay. Okay. This question about the gravitons, it's an open question to everyone on this world. If someone tells you he knows the answer, then he's lying. Because the problem is we don't really know if and how there is a relation between gravitational waves and gravitons. Like someone from particle physics would tend to tell you gravitational waves are for gravitation the same as light is for electromagnetism. So these are the bosons that are transporting the information. And therefore, the wave character is a way to describe it, but there should also be some gravitons moving along this. However, the problem starts with the fact that gravitation, as we use it today, usually, it means GR, is a classical theory. It's not a quantum theory. So in GR, actually, you cannot have, or you don't have bosons. You don't have bosons. You don't have gravitons. This is really just GR is describing gravity by saying you have a space-time, and when you have some mass or some energy, this is deformed, and this is what we see as gravity, some deformation of the space-time. So gravitational waves are also just some deformation of space-time, a deformation which is oscillating and moving and traveling with the speed of light and whatever. Gravitons, as far as I understand, are more demanding than this, because they say, for example, usually you have a certain relation between your the properties of your gravitons and your gravitation or any wavelength, which for gravitational waves does not work very well, at least as far as I know. Like the quantum physics wavelength that you would assign is not the same that you get from GR. And in general, for example, you can have electromagnetic waves which are just transporting the information of the force without any change of your system, like basically these so-called virtual photons. For example, I don't really know what this would mean for gravitation. Basically, is there some virtual gravitational waves which are connecting gravitating systems even without having the acceleration, which is what we usually need in GR for having gravitational waves? So I think there are more questions in it than answers. For sure, I'm not the right person to discuss this. I always work only in GR. That's difficult enough for me, so I don't need even more fancy, complicated theories. But yeah, these are my 2 pennies on this topic.
Okay, thank you. Could I make you a last question?
Yeah, of course.
I'm going to ask you a question that I told before to the professor who told you about a lecture about gravitational waves too. So when you have a beam of light, this beam of light can be absorbed by the medium, for example, by water. What about the gravitational waves? The gravitational wave, in my opinion, is the propagation of the oscillation of the space-time. So what's the agent to absorb the kind of wave? That professor told me something that you need to have another dimension to absorb this gravitation, and I can stop thinking about that you can use that fact to measure that other dimension that is needed for the string theory or something like that. So what I mean is being observed in some time in the universe that you have a gravitational wave and this disappear by the absorption of some other dimension or something like that. It's moving around the universe and nothing can stop it.
Observed it has not been observed, that for sure. I'm actually a bit surprised by the answer of the professor, because actually, yeah, there are these very complicated theories which have some additional dimensions, but it's not true that you only need additional dimensions to, let's say, absorb gravitational wave, because what do we mean by light when we are saying light is being absorbed? So what happens if you have some light, a lot of photons coming in, they interact with some medium, basically with the atoms usually, and if, for example, if it is very dense, like a wall or like my hand, then the photons there cannot pass through. But if you have, for example, some medium, you can see the curtain here behind me, you see there is some light going through. It's not completely blocking everything, so there is some partial absorption. And for gravitational waves, what you usually have is that you also have some partial absorption by matter. So when, for example, gravitational waves come towards the Earth, and they pass through the Earth, they are being absorbed a little bit. They're putting it a little bit amount of energy into the Earth. For example, there have been ideas to say we could observe how the moon is deformed when gravitational waves come in. This deformation of the moon, of course, requires some energy to produce the forces or to deform the moon. So there is an absorption of gravitational waves by regular matter. You don't need any additional dimensions for that. Of course, if there are additional dimensions, this could happen. This might be. But there is an interaction. The point is just that it is usually very, very weak. So it's not like for light, where most of it gets absorbed. It's just that a very small amount of it gets absorbed. That's why usually people say gravitational waves travel through the universe without interaction. There is interaction, it's just very small.
Alejandro, it was not the other professor. It was a charlatan. It was me. And the point is that the question, as I understood it, was related to the fact that the gravitational waves decay as 1 over r. And usually people think of light as decaying as 1 over r squared. And the point is that with gravitational waves, you measure the whole wave, while when you think of light, you are counting the photons. So you are talking about the dissipation of energy. And that decays as 1 over r squared. This is why I talked about, the only way of losing those waves would be by, gravity leaking towards other dimensions, but depositing energy and exciting the motion, as you just said, is of course the way to go.
Okay. So, are there any other questions? Okay, so then let's proceed with my original plan. So just to recall to you, we were talking about the different properties of a wave. We had that it has an amplitude, we have that it has a phase or a frequency, a polarization, and there are also others, but the last one I wanted to mention is the second part of my talk, the so-called modes. So what do we mean by modes? By modes, we usually, what we want to say is that when you describe a wave or you learn the wave, the simple solution is that you get just some sinusoidal, which some frequency. This might be time dependent or just a fixed frequency, but basically you just have one wave which has at a certain time one fixed frequency. However, this is not usually like the most complete solution you can get when you consider waves, because systems usually do not only emit in one certain frequency. You usually have different frequencies, and there is this special case of the so-called modes where the different frequencies are not like the blackbody radiation, where you have a lot of or like more or less smooth distribution. No, you have usually like one fixed frequency called the fundamental frequency, and then you have a superposition of different waves, where one wave has, for gravitational waves, for example, 2 times this fundamental frequency, then another part which has 3 times the fundamental frequency, 4 times, 5 times. So this is what we usually call modes, and this is what I'm going to talk about in the remainder of this talk. But before I introduce this in more detail, let's go back to a simpler example than gravitational waves, namely to music instruments, because this property of modes is something that not only exists for gravitational waves, actually, as I said, exists for every wave. And for example, for instruments, you also have usually like one basic tone. So for example, when you're a very good singer, you can do a perfect C or something like that. But usually you also have something you call overtones. What are these overtones? These overtones are exactly what I was saying by these modes. So these overtones is you have your C, what you are singing, and on top of that you have something which is 2 times your C, or 3 times your C, 4 times your C. And this is, for example, for a singer, usually what makes for us as humans hear different when they are singing, and if we think it's nice or not. Like when you have a certain ratio between how strong these overtones are, we as humans tend to say, oh, this girl has a nice voice. When it is not, then it is different. And for humans, this usually depends just like on your body structure. So these overtones are reflecting some additional information about the properties of the singer. And the same is for gravitational waves. For gravitational waves, you usually tend to have like one basic mode, which is carrying most of your information, but you have some additional modes on top of it, which are usually weaker, but are transporting you some additional information about the system. And that's the reason why I think that gravitational wave modes are something interesting. And not only me, there are also other people who believe this. This is because gravitational waves are these additional modes are giving you some additional information about the wave. And I think it's not only an interesting field for that reason, it's also an interesting field because it's a relatively understudied field. So usually gravitational wave astrophysics, as they are done up to now, and we're only considering like the basic mode or your basic tone. And now that we are starting having detections, and then we are starting having more and more accurate detections, we are starting to see that we don't only have this basic mode, but we have some additional modes, which will help us to understand everything in more detail. So, but now let's go again more to gravitational waves. What do we really mean by modes, or how can we accurately define them? Because up to now I'm just saying, okay, we have some basic mode, and you have some additional modes. When we talk about modes in gravitational waves, we usually mean something we call spherical modes. So you can define different kinds of modes. For example, there are also quasi-normal modes. Quasi-normal modes is something that usually appears after your gravitational wave has merged. These are related to the modes I'm talking about, but the modes I'm talking about usually refer to the in spiral and the time short before the merger of your gravitational waves. So, and as I was saying, like this usually work, you have some fundamental frequency and then you have some additional frequencies on top of it. And these modes are more accurately called spherical modes because they are related to their spherical properties of your system. So when you hear this like spherical modes or spherical decomposition, maybe by some of you a bell rings somewhere. Do you have an idea what this spherical decomposition could mean, or do you know some example where something like a spherical decomposition is done?
I'm sure students have seen this in nuclear physics when describing nuclear modes of vibration as well. Anybody in Cuba has an idea or remembers how you do that in nuclear?
Like, for example, in hydrogen atoms, you have something like this. Do you remember like what we use for or how we use spherical decompositions in hydrogen? Something you probably learn like in the second, third, fourth semester of your undergraduate studies.
Even if you're not for Cuba, you can reply if you want.
Again, I'm not expecting a perfect, accurate answer. I would not be able to give a perfect, accurate answer myself. It's just, again, collecting ideas.
So we're basically expanding the solution in terms of those spherical harmonic functions. Splitting of the radial part and the angular dependencies, basically.
Yes. Yes, like, for example, for the hydrogen atom, like, as I think Mark was saying.
Sorry, yeah.
Yeah, you can basically, for example, for the hydrogen atom, you say you want to solve the description of your hydrogen atom, and you find that you are lucky enough that you can divide your solution in two parts, basically in the radial part, which you usually denote by your quantum number n, so which is telling you like, are you in the ground state or in a second, third, fourth state or something like that. But on top of that, you have the angular properties. These are usually related to the quantum numbers L and M, which are related like to the spin and this. And the point is, you probably have seen like this radial part has something interesting, that it's not that you just have like spheres one on top of it. It's not like Bohr was saying in the past, where he said, okay, we have a basic state, which is a circle, we have the next state, which is a circle, we have the next state, which is a circle. No, these have different shapes. The most simple one looks like a sphere, but some maybe look like a flower, others might look like a peanut, and these kind of things. And we have basically the same for gravitational waves. For gravitational waves, when a source is radiating, we have also this, that there is some part which is because gravitational waves are 4-dimensional things, so we have some part which is the time evolution, which is telling you like how this system changes time. You have some radial part, which is basically just telling you that these things go away, and when they go away, they decay with 1/r. But you also have some information about their spherical properties. And these spherical properties is usually what we call what we call the modes of gravitational waves. This is a spherical decomposition where you say, okay, we have a source which is emitting gravitational waves, which in general is not isotropic. So the emission of gravitational waves is not equally strong in all directions. In some directions stronger, in some directions less strong. And this you can also decompose using certain shapes. And this will tell you something about the modes. So, but now the next question, of course, would be to ask, so, okay, maybe you can do this mathematically. It's very nice. Maybe it's a good way to solve your problem mathematically, but does this really mean something? Like, is there some reason why we should be interested in these modes? So, for example, for the hydrogen atom, the N number is telling you like the level of the energy. But these L and M numbers, which are related to the shapes, tell you more accurately about how likely it is that your electron is at a certain region around your proton. And for example, there are some regions which are like easier from one go to the other, like that there is a change from a certain level to the other. Pauli rules, something like this. And so for hydrogen atom, this is interesting to know this additional shape. But what about gravitational wave sources? Why do you think that like the shape of the radiation could be interesting in general? Any ideas?
Could you repeat, please?
Like, we know that a gravitational wave source is emitting radiation. This is not done. No, I forgot the word. It's not equal in all directions. There are certain directions which are stronger and certain that are less strong. Why would for us be interesting to understand in which direction is it stronger or it is less strong? What do you think we could learn from this?
The nature of the radiation source, I guess, how for example, black hole, how they're merging, the acceleration and movement of these black holes, I guess.
Yes. So basically, if you only look at your frequency of your gravitational waves, you know it is repeating. You know after a while something is repeating. And that's cool. Of course, this is extremely important to know for gravitational wave. This is related to the mass of the system. So this tells you a lot about the mass. And when you have, for example, the amplitude, you know how strong this is. How strong this is tells you, for example, if you are close or if you are far away. But basically, that's it. So now when you have also some idea of the emission, like how much is going in a certain direction, how much is going in another certain direction, this gives you more information about really the form. Like if something is repeating on a circle, then you expect, for example, that in all directions around your circle, it will look the same. But if something is, for example, repeating on an ellipse, so you have an orbit with some eccentricity, then you would at least expect to think, okay, maybe could be that in a certain direction, along the smaller parts of your ellipticity, you have more radiation, and in another direction you have less radiation. So the modes can tell you something about the, like, let's say, more subtle properties of your source. And yeah, this is why they're interesting. And in particular,
if I could ask,
okay, yeah, of course.
But how would you measure that anisotropy? You need to be in different directions from the radiation source. So that's I don't know, how could you infer that the gravitational wave is not isotropic in all directions? How would you measure it?
This is an excellent question. It's the next question I actually wanted to discuss with you, and a question that made me suffer myself a very, very long time, because as Seoane was pointing out, yeah, you say, okay, we have, like I've explained, you have different directions, and in different direction you have a different radiation. And the first point is sense, okay, nice. Then I just have to observe my gravitational wave from different directions and I can know something more. But reality is different. We're lucky enough that gravitational waves are usually not, gravitational waves are not very close to Earth, because it would destroy Earth. So actually we're lucky enough that they are not very close. But this brings the problem that you don't see the gravitational wave source from a lot of directions. You usually see only one ray. It's only one ray that is coming to you. So from this nice shape that maybe can be like something like two balls, or maybe it looks like a beautiful flower or whatever, you're only seeing one point. And from that you cannot infer really much about the rest of the shape. So, but I was telling you at the start that modes actually are defined in a certain way by frequencies. So this is what is already giving us some hint that you know that your modes are actually related to your frequency. So if you ask me how we can detect gravitational wave modes, the very simple answer would be, I could say, you measure just the frequencies. You look on your frequencies, you make some Fourier decomposition of a gravitational wave that is coming in, and you say, okay, I have certain amount of the basic frequency, or which is 2 times the orbital frequency usually, certain amount of, or an amplitude for something which is 3 times the basic frequency, something which is 4 times. However, this is a Fourier decomposition, and this is what makes the detection of gravitational wave modes somehow difficult and also subtle. Because what happens? Actually, if you would ask a theorist what are Fourier modes of gravitational wave and what are spherical modes of gravitational wave, he would say, okay, these are 2 completely different concepts. These are 2 things. One is a decomposition of its shape. The other is the decomposition of the wave by its frequencies. However, if you would ask an experimentalist, many experimentalists would tend to say, like, these are basically the same. This is because from all the compositions that you in principle could take to describe the shape of your source, the one that has been chosen are the spherical, the one using spherical harmonics, because it gives you particularly simple solutions, in the sense that as long as your source is a circular source and you have no spins, you can basically say your spherical modes are exactly the same as your Fourier modes. So your quadruple mode of your source corresponds exactly to the Fourier mode with 2 times the basic frequency. So you can do this detection by saying, I want to know something about the shape. I cannot see really the shape, but I know how the shape is related to the frequency that I can see. So this is usually the way to go. Of course, as I was saying, this is for the very simple case of a circular orbit and no spins. When you have, for example, an eccentric orbit, or if you have spins, this change a little bit. You don't have this simple relation anymore. You still have some relation that you say, okay, for example, your quadrupole mode is related to something with 2 times the frequency, plus maybe some smaller amount with 3 times the frequency. And for your next mode, you have something with 3 times the basic frequency, plus a little bit of 2 times and a little bit of 4 times your frequency. So there it becomes more complicated, and you cannot do this simple relation of just saying, okay, my Fourier modes are the same as my spherical modes. But what we do there is that, okay, gravitational waves are usually anyway detected using some templates, which is some theoretical prediction. And what you then try to look is what of my theoretical predictions, including spins, including eccentricity, or including mass ratios, these kind of things, is the most similar to the gravitational which I'm detecting and which I'm basically describing in Fourier modes. So to summarize what I was saying is basically you cannot really detect spherical modes, or you cannot detect them, strictly speaking, but you can use a relation, a theoretical relation, which you can predict between spherical modes and Fourier modes to then try to detect them.
Yeah, I have a question.
Of course.
Is there some relation between this anisotropy in the intensity of the gravitational waves and the mass density distribution in the body?
Okay, I guess by intensity you mean something like the amplitude of the wave. Yes. Okay. Yeah. Of course. Basically, the relation, or the simple relation, is that your modes, like your spherical modes, are equal to your multipoles. So really to the mass and the current multipole of your source. So each of these modes, which describe its shape, is also really related to the properties, to the dynamical properties of your source. If you talk about the amplitude, then the amplitude that we're really detecting is just as you are summing up all of your different modes. So the relation is more or less, if some particular mode, for example, the quadrupole mode, is very strong, then it will give you a strong contribution. And if you have a little bit of the octupole mode, this will come on top of it. Of course, because these are waves with different frequencies, they don't simple sum. They just don't just sum up to a new amplitude, which is the sum of both. No, it's a superposition. But yeah, there is, of course, a relation.
I have a question.
Yes, please.
Have you been seeing in the gravitational wave any cutoff or resonance mode?
Okay. Resonances, yes, usually like, I mean, for example, I was saying there are these spherical modes, but there are also these quasi-normal modes. Quasi-normal modes are very closely related to spherical modes. This also represents some spherical decomposition, but quasi-normal modes actually exactly describe resonances, because what are quasi-normal modes? Quasi-normal modes is basically when you have 2 black holes, let's say, to keep it simple, which are merging. You know that right after the merger, because they are previously there are two spheres, especially like if, let's say there are two Schwarzschild black holes, so they're basically two perfect spheres. But after these two spheres touch each other, they are not a sphere immediately. This is something deformed, which looks more like a weird potato or something like that. And because black holes want to become black holes again, this deformed potato tries to get back to some sphere, so to become again a regular black hole. And to do this, it needs to get rid of additional curvature, actually, that you are having there, or of energy which is too much there. And this is done by emitting gravitational waves. And now these gravitational waves which are being emitted basically represent exactly some resonances, or like the way to compute it is to take a perfect black hole which you perturb, and you look this perturbation, which resonances are excited. And yeah, this is, for example, how, or one way how modes can be related to resonances. You have other cases, for example, again, in the case where you have a perturbation where you say, okay, you are considering an extreme mass radiance pair where you have a very big black hole and a tiny black hole moving around. What this tiny black hole is doing, or a way to understand it, could be to say, okay, this is also perturbing your big black hole in a way, and it's exciting some resonances into it. I think, if I remember well, these resonances are not directly related to the modes I'm talking about, but there are also some kind of resonances, and you also have some particular frequencies which are getting excited.
Professor, what about the cutoff? Is there any case that you have a body and the gravitational wave is coming to this, and there is a cutoff frequency, and this body doesn't feel the gravitational wave effects?
I cannot really, I mean, I can tell you that I think, yes, probably there exists something like this. But honestly speaking, I don't know in which cases this can happen. I can imagine that, for example, you have a black hole and gravitational waves are coming in. Gravitational waves are perturbing this black hole, and there are certain gravitational waves which maybe will just pass by without doing much. Some which will get completely swallowed without having any particular effect, just like falling in. And this will depend on the frequencies, and there could be some kind of cutoff. But I'm just speculating. I've never touched this question myself.
When you told me before that there is many resonance modes, are you relating this to the classical physics? We are talking about GR. So if you say that you are going to have resonance modes, so in certain way, you are telling that the black hole, for instance, is oscillating to certain frequency and is deforming the space-time in certain frequency. It doesn't mean yes. the gravity is the gravity is not a continuous formation of the space-time and just a moment, another moment. No, I mean the body is deforming in some frequency the space-time, not continuously.
Can you please repeat what you were saying? It was a bit cut off, and so I couldn't hear it very well, and so I'm not sure.
Okay, I'm going to repeat my question. Yes, when please. You have a resonance mode, for instance, in a bridge in the planet, and some error comes, the bridge is going to go on and go, you know. And if you say that you are going to have a resonance mode in a black hole, it doesn't mean it means that the black hole is producing a deformation of the space-time at a certain frequency and not continuously, as I think it is.
Okay. Okay. It's like in general for resonances, it's not that you have either a resonance or you have no resonance. Usually, it's that you have like some frequencies which are very strong, and then it goes down smoothly. And so when the gravitational is coming in and the black hole is being perturbed, the black hole is in a sense like a kind of bell, or like you can imagine like for a bell. And so you can take your bell and hit it in a very weird pattern. And then of course the bell is going to ring, but maybe not very strong because you are not or the system is not really in resonance, or when the fitting or one of the excitation that fits very well, you can excite the ringing of the bell very well. And for black holes, it's similar. Like it's not that there are just some frequencies which are going to cause perturbations or resonances. It's just that some of them do it stronger than others. I don't know, like if this answers your question.
I think this was more or less explained. There might be some confusion here, because this is something that Leo explained on the first day. So if I might say just a few things,
yeah, of course.
Alejandro. So like I think was Benny who was asking, I don't know. But as like in the Schwarzschild case, the periapsis processes so that you if you have a spin, if your black hole is spinning, which is the most general case, the one that Alejandro was considering, you need to introduce two additional frequencies. One is related to the radial motion, the time to go from periapsis to apoapsis in the orbit and back. And the second one is linked to the azimuthal motion around the spin axis. They require time to describe 2 pi around it, which is the time for the azimuthal angle, which is usually called the pi, to increase 2 pi radians. These three fundamental frequencies and their harmonics are responsible to make so-rich information the kind of sources that Alejandro was talking about before, extreme mass spirals, because you have a very large mass ratio. And the larger the mass ratio, the more cycles you have, so that these frequencies stand a very important chance to show up in your detection. They allow you to probe the geometry around the supermassive black hole with gravitational radiation. I don't know whether this helps you in any way.
Okay. Yes, please.
I have a answer to a previous question. I think the difference between different direction of gravitational waves may be measured on different point on the Earth, so that we can get the distance of that gravitational wave source. So is this okay?
Yes, like I think you felt like, for example, that LIGO and Virgo, they're on different points of the Earth, like in Europe and the US. And you do this parallax that you say, okay, because gravitational waves we assume are traveling with the speed of light, and they will reach at different points, and you can use this to not to measure the distance actually, but more the sky location. This can help you to constrain the sky location very well. However, for like the point of modes, the problem is that also these are different points on Earth, and for us, these are huge distances. Because the source is so far away, it still basically looks like a ray coming from exactly the same point, even if you are on different parts of the Earth. So for the measurement of modes, this is unfortunately not helping much. But for other reasons, like as a parallax, this is, yes, a very important point in gravitational wave detection.
In which point it is important?
For example, to restrict your sky location, like you have a gravitational wave coming in. Gravitational wave detectors, they don't see equally well in all directions, but they see quite well in almost, or in a lot of directions, because it's not like a disk where you're trying to catch photons, where you know, okay, if it is pointing in that direction, from there it's coming in. No, you have some L shape, and if a wave is coming in from here, it can excite it. If it's coming from here or from here. So when you only have one detection, it's usually quite difficult in gravitational wave detection to know where it is coming from. But now when you have two detectors, which are very far away, you can use this fact that you say, okay, here it arrives at a certain time A. At the second detector, which is maybe further away from the source, it reaches a certain time B. And by this time difference, this can help you to constrain the direction from where the gravitational wave is coming in.
Okay. And I haven't understood much about that overtone. So.
About what? Sorry?
Overtones.
These modes and overtones, it's as I was saying, it's different because this is related, like they're related to the shape of your source. So, for example, if your source is a sphere, or if it's something more like a peanut, which is usually what it happens, you get information about your modes. However, because you're only seeing, like, if you would be very close, like if my head is the Earth and the source is here in my hands, then I'm close enough that I probably could see this upper part and this lower part very well on Earth. But what actually happens is that these sources are very, very far away, usually parsecs, kiloparsecs to megaparsecs. So from all this emission that is coming out, we only see one ray coming to the Earth, and this only one ray cannot really tell you much about the shape, because it's only one point of your whole directions. But as I was explaining, what we usually do is we know that these spherical modes or these shapes are related to certain frequencies. So by detecting the different frequencies, the Fourier decomposition, we can infer information about this shape, although we are only seeing one ray. But this is independent of how many detectors you're using. Or it's not really independent. If you really go into detection, you will see that there are some reasons. But from a theoretical point of view, it's independent of if you have one or two detectors on Earth. It's just the fact that you detect different frequencies, what you're using.
Oh, so different frequencies tell us the shape? Or?
Yeah, you can infer basically the shape from the different frequencies. It's not a one-to-one relation, but with good models, good theoretical models, you can infer which shape your source should have. So, and this is something you do in general for gravitational waves. Like when the gravitational waves come in, this tells you some information. But what we really do is usually we take some theoretical prediction and compare our theoretical prediction to what is coming in. And then we say, okay, this theoretical prediction fits our data the best. So this must be the properties of the source.
And that different frequency at different points or at the same point?
The different frequencies coming from the same point, yes. Like a ray, like a gravitational wave, is a superposition of several harmonics. So every gravitational wave contains different frequencies.
So from modes, we find which shape is is the most possible, and
yeah, basically.
Okay, thank you.
You're welcome. So, yeah, are there any other questions?
Just keep in mind that it's been 1.5 hours by now.
Yeah, yeah. I'm coming to an end, or maybe if you guys want to have some rest before the next talk, I'm also fine to finish now. So I have some more examples, but I think the most important part is said.
Excuse me?
Yes.
It's something you said before when you were talking about how lucky we are that Earth is far away from gravitational wave source, that we could be destroyed, or I don't know, by that gravitational wave. That is like a curious question. Is that the math done? How close we need to be near a gravitational wave source to experiment a real and noticeable effect in the composition of the habitants of the Earth or the Earth itself? And how? What could it be?
Can you please repeat the question? I don't really understand.
What could be the effects of the gravitational waves on our planet if we were close enough to a gravitational wave source, and how close we need to be to it? So how strong are the gravitational waves when they are created, and if that would cause you harm to ourselves? I don't know.
How close we need to be, actually, I don't know. I mean, you can compute this, of course, with your theory, but I've never done it. Now, the point I was saying is basically because for example, what I was telling at the start, that when a gravitational wave comes in and you have point masses, then these point masses are for a moment like stretched away and quenched in the other direction, and then again doing something like this. And this is also exactly what happens with the Earth, for example. Our Earth is a sphere, and when gravitational waves come in, actually it's being deformed a little bit. However, gravitational waves, how strong this deformation is, it's extremely small. It's usually, I think, like smaller than the size of an atom. So it doesn't have much to the Earth. However, imagine that because gravitational waves decay with 1/r, so if r is very big, 1/r is of course very small, but if you get closer and closer, then this deformation could become stronger and stronger. And now you can think yourself that imagine our Earth is moving a little bit around, and the more this moves around, of course, because our Earth is to some extent rigid, so it's not perfectly elastic, and you can deform it and stretch it and it will come back to its form. No, after a certain while, this of course could be strong enough to cause deformations that are that could excite, let's say, our Earth too much and cause some physical damage. And that was basically what I was saying. Like, okay, we're lucky enough that we are not too close because like the excitations could be too strong. For example, like some maybe stupid analogy, but imagine you have a bowl of water. You can move this bowl of water a little bit and you will get some waves and everything is fine, you get some resonance. But if you do it too strong, the water will just go out of the wall and will basically destroy your nice simple bowl. If you would happen to be really so close to the merger that you are not even seeing the waves, but you're really being swallowed by the merger, then of course everything can get extremely violent, because you must understand that gravitational waves are being formed really by bodies that are deforming space-time itself so much that at the end, although we are megaparsecs away, we are still seeing some effect. So as for water, like if you move water a little bit, then you have some waves, but they decay very fast. If you can see waves really far away, this is usually because it's something very strong, something very violent. And this is actually what is happening. It's happening for the space-time. And because we are beings living in space-time, if what we're living in gets disrupted, pulled, stretched, very violent, we of course would suffer from this and probably get destroyed at the end.
Thank you.
Okay. Any other questions? Also from non-Cuban students. We have had a few, but maybe some other people want to ask something. No? This is your last chance. 3, 2. Okay, well, in that case, yes, because the other day we ran into this problem that we had only one speaker because he ate all of the time. If you're fine with that, let's stop here.
Yeah, for me, I would like to go to bed, so I'm perfectly fine with finishing this.